The electron configuration for fluorine is 1s2, 2s2, 2p5. This is what the orbital notation looks like. The principle that I'm going to be explaining is the Aufbau principle, which states that in a ground state of an atom, electrons fill atomic orbitals of the lowest energy levels before occupying higher levels. The way this works in fluorine is how the previous shell is always completely filled before moving on to the next shell. For example, 1s2 is prioritized over 2p5 because 1s2 has a lower energy level, so it is filled completely and 2p5 is not because it is higher. The electron configuration for copper is, in brackets, argon, 4s1, 3d10. This is what the orbital notation looks like. The principle I'm going to be explaining for this configuration is the Pauli exclusion, which states that there cannot be more than 2 orbitals in a shell, and they have to be opposite spins. Every orbital in copper has 2 orbitals in its shell, the only exception being the s block, with 1 orbital. The copper configuration also has opposite orbitals, with none of the same spin for each shell. None of the shells have 2 of the same spinning orbital in them. The electron configuration for cerium is, in brackets, xenon, 6s2, 4f2. This is what the orbital notation looks like. The principle I'm going to be explaining is Hund's rule, which states that every orbital in the sublevel is singularly occupied before any orbital is doubly occupied. This is showed by the F block not having a full shell, but rather 2 open shells. Because there are 7 shells in the F block, there cannot be any full shells before there are 7 shells. Because there are only 2 orbitals, there will only be 2 shells with 1 orbital in each.